Check it out. I never loved nobody fully. Always one foot on the ground. And by protecting my heart truly, I got lost in the sounds I hear in my mind. All of these voices I hear in my mind. All of these words I hear in my mind. All of this music, and it breaks my heart. And it breaks my heart. And it breaks my heart. When it breaks my heart. Suppose I never ever met you. Suppose we never fell in love. Suppose I never ever let you kiss me so sweet and so soft. Suppose I never ever saw you. Suppose you never ever called. Suppose I kept on singing love songs just to break my own fall, just to break my fall, just to break my fall, just to break my fall, break my fall, break my fall. All my friends say that of course it's gonna get better, gonna get better, 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 better. I never loved nobody fully. Always one foot on the ground. And by protecting my heart truly, I got lost in the sounds I hear in my mind. All of these voices I hear in my mind. All of these words I hear in my mind. All of this music, and it breaks my heart. And it breaks my heart. I hear in my mind. All of these voices I hear in my mind. All of these words I hear in my mind. All of this music, and it breaks my heart. And it breaks my heart. And it breaks my heart. When it breaks my heart. When it breaks my heart. When it
All right, so welcome back. Today we're going to continue on algorithms and algorithm analysis. We stopped, we were looking at each one of these steps in detail. We looked at some subtleties with respect to identifying the input, some subtleties with respect to identifying the input size, and now what about the elementary operation? Well, I mean, there can be many different elementary operations, right? Ultimately, you only want to focus on one operation because you want to keep it simple, right? There could be, you know, additions and comparisons and node traversals, et cetera. Focus on one. And when you focus on one, you generally focus on the one that's most expensive, the most common, or the most relevant to what you're trying to do. And there's not any one answer here either, right? You could be analyzing an algorithm with respect to time, and then you would look at maybe a comparison. You could look at it with respect to memory, and you'd look at it with respect to swaps, all right? The memory accesses or something like that. But generally, you do not consider operations that are necessary for the control structure of the algorithm. In other words, consider a traditional for loop. For int I equals 0, there's an assignment. I is less than n, that's a comparison. I++, that's an addition. We do not usually think of those as our elementary operations because those are necessary for the control structure of the algorithm. Inside your loop, you're doing something, presumably, right? If you're not writing anything inside the loop, then why'd you write the loop? But whatever you're doing inside the loop is probably far more important than the loop itself, right? Some classic examples that we've already seen here, of course, are comparisons. Arithmetic operations like addition, subtractions, multiplications, divisions, and then linked list operations like node traversals. Why did I put additions and subtractions, why did I group those as the same? Order of operations, but also, is there any difference from a computer's perspective?
Oh, no.
Right, why? What's a subtraction? It's an addition by a negative number. What about a multiplication, division? What is a division? It's a multiplication by a fraction or reciprocal, right? So those are actually the same operations as far as a computer is concerned, right? So the second to last step here, the penultimate step, is the actual analysis. And this is where, art comes in, right? How many times is the elementary operation executed with respect to the input size? And basically, you're going to come up with a resource function. And hopefully, you've seen enough mathematics that you understand this symbol. All right. First of all, let's go ahead and review. Right. So when I've got a symbol like this, first of all, what is that thing? Natural numbers, right? And so 0, 1, 2, 3, right? Despite what grade school or high school algebra told you, we do include 0, right? Why? Because you need an additive identity. Without it, you do not even have a semigroup, modern algebra, right? Anyway, R, those are real numbers. And so if I put a plus up here, this is or a positive reals. So why am I considering a time function here from the natural numbers to the positive reals? Consider a regular old, a regular old Cartesian plane here, x and y, where all of them are reals to reals, right? Reals to reals. Well, first of all, have you ever heard of an input size of 3.5 elements in an array? No. So, have you ever heard of an array with -10 elements? No. It doesn't make any sense. And so what we're going to do is we're going to restrict our domain, right? This is what this is called. The domain is going to be restricted to integer values, right? You can have an array of size 0. You can have an array of size 1. You can have an array of size 2, et cetera, et cetera, et cetera. We're going to cut off this entire half right here. And we're going to cut off all fractions. Now, why am I only considering positive reals here? What if I considered a function that looked like this? What does that mean in the context of algorithm analysis?
It's going back in time.
Yeah, it's going back in time, exactly, right? It's a negative value. You start your computer now, and then you have your answer 10 days ago or 10 seconds ago. It doesn't make any sense. So we're only going to consider monotone increasing functions, squared, right? Linear, quadratic, right? Or exponential or whatever. Weird. All right, so that's what we're going to come up with. That's why we're restricting our consideration to a resource function here. It may consider some art, or it may require some art, some summations, other calculations, finding closed form solutions, or maybe even super advanced math, right? As in like first derivatives and L'Hopital's law. It's not super advanced. But generally what you want to do is you want to consider the worst case scenario. You want to provide an upper bound on the worst case running time of your algorithms. Here's an example. This is something that we do in Computer Science 1. Where is it? Linear search. There it is. Okay. Here's some pseudocode implementing a linear search algorithm. Oh, sorry. Thank you. Yeah, just go ahead and yell at me. All right. There we go. All right, so let's go. Yeah, sorry, what?
I don't want to hurt your feelings.
Oh, okay. One, let's go through our step-by-step process here. What is the input? Well, here is one of those areas where you actually have two inputs, right? So which one should I focus on, the collection or the key? Probably the collection. Why? Because there's a big difference between a collection of 100 elements and a collection of 100 billion elements, but there's only ever one key. That's the most relevant. 2, what's the input size? I encoded it as part of my pseudocode. N, the number of elements in it. Another thing to notice here is, where did I start my indexing? 1. Why? Because it's mathematical, or it's pseudocode, right? So for each element in the collection A, if A sub I is equal to our key, then we output A sub I. Otherwise, at the end, we output phi. Why didn't I output null? Null is a language-specific construct, right? If you were in C, it would be all caps null. If you're in Java, it's all lowercase null. If you were in Python, does anybody know?
Not for camel case.
None. There is no null in Python, it's none, right? All right. What's our elementary operation here? So again, you would end up writing a traditional for loop for this, right? For I equals 0, I is less than whatever I plus plus. We're not going to ignore, we're going to ignore that because we're doing something inside the loop here, right? All right, so how about this output statement? That's the end of the algorithm. You only ever do that once. So I'm going to say that it's the comparisons, comps, online, what is it, 3? There we go. Oh, is it 2? Oh, thank you. 2. All right, so the analysis here. We're going to consider the worst case scenario, but before we do that, let's go ahead and consider the best case scenario. Under the best case scenario, how many comparisons do you make? You get lucky, right? 1. Right, you find it the first place you look for. A sub 1 is equal to your key.
Oh,
right?
This is search.
Yep. What about the worst case?
You search through the entire list.
You search through the entire thing, and either you find it at the end, last thing that you looked at, or you don't find it. So, N. And I left a big gap in between there. Why? What else could you consider? All the cases in between, so right in between, I'm going to call that the average. Now, a naive way of figuring this out is just to simply take the best and the worst and divide it, and you get n divided by 2. The more sophisticated and mathematically rigorous way to do this is to define a probability distribution on successful searches, maximize that distribution for the number of comparisons, come up with a summation, solve the summation, and guess what? You end up with that. Right? So we're not going to do that. But think about this in terms of a graph. Come on. Got to be at least a little bit straight for it to go straight. There we go. All right. So what does n look like as a graph? Like that. What does 1/2 n look like? Like that. Is there really any difference between these two functions? No. From a calc perspective, what was the first derivative of n? 1, a constant. What's the first derivative of 1/2 n? 1/2, a constant. Right? These are both linear functions. They have both the same rate of growth. This constant out front here, who cares? Because if you upgrade your hardware, there's another hidden constant out front here, see, that is actually capturing the time that it takes to do a comparison on that particular computer. So just go ahead and take that 1/2 or that 1 and incorporate it into C, right? And these are exactly the same. Right? Change it to a different hardware. Upgrade your hardware to the latest, right? And now it's 3 times as fast. And so now there's a 1/3 out front that wasn't there before, okay? So no, there's no difference between these two. So average versus worst. What I'm going to do is I'm going to focus on the worst case scenario. Because I don't care about the average. What if I have an algorithm that, on average it executes in 5 seconds, right? That's because that 99% of the time it executes in 4 seconds, but 1% of the time it ends up taking you billions of years. Does that sound like a great algorithm? Probably not, right? So I'm going to want to put an upper bound, an absolute upper bound on the algorithm's performance before I run it, because I want to guarantee that this thing is actually going to run, right? All right. So that's our 4 or 5 step process. We're going to skip 5 here until the end. Let's get some more practice with some actual examples, okay? So examples. Let's go ahead and use selection sort. as an example, and then we'll do insertion sort as an example. We already did, of course, here, linear search. And now we remember why it's called linear search. Why? It's linear, regardless of how you look at it. Right? By the way, can you always think about the best case scenario? No. Almost never could you take that as the best case scenario. Right? The best case scenario, just shut your computer off, and now you don't have to worry about time at all. Right? All right, so we've already taken a look at linear search. Let's look at selection sort. Now, just let's remind ourselves of what this looks like. And to do that, let me go ahead and give myself an example array here. There we go. So how does selection sort work? Let's think about this as the first iteration. Right. Remember, it's called selection sort for a reason. What do? The operation is that you go through and you find the smallest element among elements 0 through 8, or in general, 0 through n minus 1. Or if you want to pseudocodize this, you would then change this to 1 up to 9 instead. Right? I'll go ahead and keep it 0 at least for this one. Find the smallest element. Okay, well, that's pretty easy. 42. We'll start by thinking that 42 is, 42 is our smallest element. Right? And then we go to the next one. 4. 4 is even smaller, so that's our minimum now. 9 is not less than 4, so 4 stays the minimum. 4 is not less than 9, or 4, excuse me, so that first 4 stays our minimum. Not less, not less, not less. We found something less, so we update our minimum. That's even less, so we update our minimum. Now what do? We swap it, swap the min with a sub 0. Right? And here again, I'm doing 0 indexing. Say again?
You swap it with the head.
Well, with the first one, yeah, because this is iteration 1. What about iteration 2? Once I've done this, let me go ahead and fat finger this, 42 and 0. There we go. 42 is now over here, and 0 is right here. Do I re-examine 0 at any point? No, because it's where it needs to be. It's been selected and put where it should be. So in the second iteration here, what do? I find the min among elements 1 through n minus 1. Right? And then I swap it, the min, with a sub 1. Right? Generalize this, dot, dot, dot. On the ith iteration here, what do? I find the min among I dot, 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 n minus 1, right? I plus 1, whatever, right? And then swap with I minus 1. Swap the min with I minus 1. So you get the idea, okay? Here is some pseudocode. We're going to implement this here in a second, just for extra practice. But here is some pseudocode that realizes that. Right? Now, here I am using 1 indexing because this is pseudocode. So I've got my outer for loop here that repeats this several times. We only go up to n minus 1. Why? Because think about it more generally. If I've got this array right here, right, and I'm on the ith iteration, I'm considering elements I plus 1, all the way up to n. What about these elements right here? I through I minus 1. These are sorted. You are done. Leave them alone. Fast forward to the last iteration. What do you have now? All of these are sorted. But what about this last element here, n? If the first n minus 1 of them are sorted, what about the last one? It's been sorted, right? Exactly. So I stop short at n minus 1. In the inside, I assume that the ith one is the minimum, and then I go through I plus 1 through n, and if I ever find something that is smaller than the minimum I've found so far, I update the minimum. At the very end, I swap them. Okay? So, let's go through our step-by-step process here. 1, what's the input? The collection A. Size is n. 3, what's my elementary operation?
4.
It's what's on 4?
The comparison.
Comparison on line 4. I agree, and we'll go ahead and proceed with that. Consider, however, an alternative. What's another perfectly valid answer if your concern was more memory instead? Swapping. Reading and writing. Writing to memory is actually more expensive than reading from memory in a lot of cases, right? And so if you wanted to minimize this with respect to, you know, swapping things out of memory, you wanted it to be as stable as possible or something like that, then you might want to look at it from the perspective of swaps. Right? All right, but I agree. Let's go ahead and go with this one right here. There we go. My comparison. Now, how do we go about counting up the number of comparisons in this algorithm? I'm going to go and focus on lines 4 through 6 first. Okay? Now, how many times is that comparison executed with just those lines, ignoring everything else? 1. Okay? And that's lines 4 through 6. Okay? Now, bring out your focus a little bit more and realize that that's inside of a for loop. How many times does that for loop execute? It executes for I plus 1, I plus 2, I plus 3, I plus 4, dot, 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 up to n. How many is that? Let's go ahead and set up a summation, and then we'll worry about thinking about that later here. N minus
1.
nope, careful. So let's set up our summation here. J is running from I plus 1 up to and including n. Right? That's lines 3 through 6, or 3 through 7 now. Right? Within that, we have yet another for loop. And so that's going to be another summation. And it's going to run from I equals 1 up to n minus 1 of this entire thing right here. Okay? You're partially right, sure, right? So let's go ahead and solve that summation now. You could throw this into Wolfram Alpha, you could throw this into MATLAB, or you could throw this into anything and it'll solve it for you. Let's get some practice solving this by hand though. Right? So the summation was I running from 1 up to n minus 1, and then there's a summation in that. It's a double summation. J is equal to, what was it again? I plus 1 to n? And we were summing 1 inside, okay? Let's go ahead and get a hold on this inner summation first, because that's easy. This thing is equal to 1 plus 1 plus 1 plus dot, 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 plus 1. How many times? And careful, it goes up to n. I agree with that, n. But where does it start? N minus I, okay, you jumped right to the end. Where does it start though? I plus 1, I plus 2, I plus 3, right? Plus, dot, dot, dot.
2, 3, 4, 5.
Yep, 1, 2, 3, dot, 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 up to n. Not n though, right? If you were to start at 1, 2, 1, 1, 3, 1, plus, dot, dot, dot. And then you went up to n, but not including I, right? I agree, this entire thing is n. But we skipped the first I of them. Right? And so what's remaining over here? This part. N minus I. Okay? So this leaves us with I running from 1 up to n minus 1 of n minus I. Okay? Summation of sums is equal to the sum of summations, meaning that you can break this apart into two summations. I equals 1 up to n minus 1 of n minus summation of I equals 1 up to n minus 1 of I. Okay? This first one's really easy. It's n plus n plus n plus n, and we do start at 1 and go up to n minus 1, so it's equal to what? N times n minus 1. Good. That second one is a little bit harder because it's 1 plus 2 plus 3 plus 4 plus 5 dot 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 up to n minus 1. That sounds familiar. Do you remember the guy? Gauss. Right? The summation of natural numbers, I 1 up to 1 blah blah blah, is equal to n times n minus plus 1, excuse me, all over 2. We don't go up to n. We only go up to n minus 1. So if you substitute n minus 1 here and n minus 1 plus 1 here, then this becomes n, and we've got n times n minus 1 all over 2. The second one is half the first, so subtracting it would give me n times n minus 1 all over 2. Looks really familiar. It's exactly the same performance as that crappy index-based search algorithm on a linked list. Right? Why? Because it's basically the same operation. Right? Okay, what is the most important out of all these? N, 1/2 n minus 1/2 n. Oh, squared, sorry. There we go. The square part, right? The lower order term, who cares? The constant out front, who cares, because that's dependent on the hardware as well. Right? And so this is a quadratic selection sort is a quadratic sorting algorithm. Now, we didn't even do an empirical study here at all, right? This is all just by looking at pseudocode and going through our 4-step process here. I can predict that this is going to be a terrible algorithm. Just for more practice here, let's actually demonstrate it. Right? So public static void selection sort, right? And we'll take a list of integers. Right? Foo. I'll just call it list. Don't get fancy. Don't get jokey. Right? All right, so let's take our pseudocode here and translate it to Java code. And for that, I'm going to go ahead and erase all this to make it clearer. There we go. All right. So my outer loop here is going to run from 1 up to n minus 1. Be careful, this is pseudocode. So we are starting indexing at 1. So I need to adjust for this. I need to go from 0 up to and including n minus 2. So for int I equals 0, I is less than or equal to n minus 2. Right? But a better way of doing that is strictly less than n minus 1. And of course, what's my n here? If you want to, we can go ahead and put it into a variable. Int n is equal to list dot size. There we go. So that I can exclusively talk about n, I++. Now what I'm going to do here is find the min amongst elements, what is it? J equals I, or amongst I up to and including the last one, which is n minus 1. Right? So I will, 1, assume that the ith element is the minimum. Right? And for this, I'm going to use the min index, so int min index instead of the actual min value here. Min index is going to be, start that at I. Right? And then for int j running from I plus 1, or j is less than n, j plus plus. If you find something that's less, list.get j is less than list.get min index. There we go. If. There we go. If the jth element is less than what you've found so far, then update the min index to be j. At the end of all of this, swap lists of I and lists of min index. Right. Now over in my pseudocode, that was a one-liner. Right? because I'm using plain old English, right? I assume that you know how to do that. Put one into a temporary variable, take the other one and put it back over there, and then take the temporary variable and put it over there. 3 lines. Right? Can I do it in 1 line? There's like an old trick that you can use, but I forget what it is.
Technically you can, you use a line feed.
Well, you'd still have semicolons everywhere, so you could still do it. But let's see. Int temp is equal to list.get I list.set element at min I to the element at min index. List.get min index. Then list.set min index to temp. Is that right? Take I, put it into temp, that frees up I so that you can put min index in there, and then put back into min index temp. There we go. That looks good. Let's try it on a very small array of 10 elements here. I'm going to load them up with random values, sort them. So selection sort of my list, and then let's just go ahead and print it out to make sure that it's actually working in ascending order. There we go. Looks like it to me, even though these are really large random values, who cares? Right? Okay, I do not want to print them out anymore. Right? But the other thing that I wanted to mention here is there are languages that you can do that kind of stuff in 1 line. If you want to swap A and B in, say, Python, A, B is equal to B, A. No semicolons in Python. So you can do something like that in Python. All right? So let's see if the empirical results of our testing here match our expected results of n squared behavior, okay? With 1,000, it took 0.024 seconds. Let me go ahead and bring, I'm gonna go ahead and write that down over here. 1,000 took 0.024 seconds. All right, I'm just going to go ahead and record that over here. Now, let's predict, from our theoretical analysis, if we go up by an order of magnitude here to 10,000 elements, how would you predict this behavior to be? So, remember that it's n squared. So if I go to 10n squared, that's equal to 100 times slower. So, my thoughts here is it's going to be about 2 seconds, 2.5 seconds. Let's find out. All right. I did save, right? Save. Let's run that again. Okay. So it's smaller, or it's, sorry, did I say? Yeah, this is only 10 times as slow, right? 191, so 10,000. All right, so I was wrong. Maybe it is an efficient algorithm. Right? If I go up by another order of magnitude here, actually, I'm not going to do that. I'm going to go up by an order, I'm going to double it, right? 20,000. Now, if I only double it, then what should it do? If I go from n squared to 2n squared, then this should be 4n squared. And so 4 times 0.01, what would that be? Like, yeah, it would be a half a second? Or a full second, right? Okay, almost there. 0.799. This is 20K. Let's go up by another increment here of up to 40. So this is 4 times as slow. So it should take about 3 point something seconds. 1, 2, 3. There we go. Almost 3. 0.2924. Right? So the exact numbers are not coming out, but the trend is. Let me go up by an order of magnitude here to 100,000 that I was kind of not wanting to do before. Remember that 1,000, or that if I went from 10,000, which is 0.2 seconds, up to 100,000, that's going to be 100 times slower, and so therefore it should take about, what, 10 seconds, 20 seconds? We'll go ahead and run it in the background here. Right? It's doable, is why I was reluctant to do it, but it's definitely going to be noticeable. Maybe we've hit a crossover point here where, okay, there we go, 20 seconds almost, to the dot, right, from our theoretical analysis, okay? Is that at all reasonable to sort 100,000 things in 20 seconds? No. Why? Because I've done it with collections.sort list in how many seconds? 0.097, right, over and over and over again. If I go up by an order of magnitude here, this should take at most maybe 1 second here. Yeah. Because I know what the what algorithm is actually being used here. It's probably it's what's called Tim sort. It's a modified merge sort. We'll talk about that later. Right? But my implementation of selection sort is not at all reasonable. If I did that with 1 million elements, what would I expect? Remember, it was 20 seconds before, so 100 times 20 seconds is going to be 2,000 seconds, which is 30 minutes or so, more than 30 minutes. I'm not going to do that. Is there a better way? Let's consider another sorting algorithm here, right, to get more practice. Yeah, go ahead. No? Okay. No?
Let me guess. Is it quick sort?
Nope, not yet. We'll do that later. Right. So,
BOGO sort?
no, BOGO sort is even worse. BOGO sort, if you've never heard of it, is you randomly permute it and then you check to see is it sorted. Then you do it again. Then you do it again. It's a joke algorithm, right? And so you would, even if you didn't repeat any permutations, you're talking about n factorial. Right? And when you get up to, say, 100 elements even, that's more than the atoms in the universe or whatever.
Yeah.
Okay.
Counterpoint, it's the most efficient algorithm because it has the best efficiency of n.
Okay.
So, I don't know.
All right, so what I'm going to observe here is that some of this stuff seems to already be sorted, right? For example, if I just looked at this one right here and I ignored everything else, it's sorted by definition, right? Now let's look at the second one here. So let's consider these two right here. They're not in order. So let's go ahead and swap them, right? And now what I would have is 4, 42, 9, 4, dot, dot, dot. Right? And these two would be sorted. Let's look at 9, right? 9 is out of order. So what we would do is we would swap these. But at that point, I would have 4, 9, and 42, and then the rest of it, of course. Do I need to make any more comparisons down there? One more comparison to see that it's where it needs to be, right? Let's think about this more generally. What if I had a section of my array here that was sorted, right? And I'm going to consider the ith element here, and this is unsorted, right? Do I need to select I or compare it to everything to put it where it needs to be? Right? I could compare it to this one, to this one, to this one. If it happens to be the minimum, I would end up shifting it all the way down over here. But maybe I can get lucky and it's not. Right? Maybe it's already in order, in which case I would only need one comparison to see, don't do anything. It's where it needs to be. Right? Maybe I only need to do 1, 2, 3 comparisons to insert it right here. Right? And then the rest of the stuff, who cares? Right? It's in order already. So I can get away with maybe some fewer comparisons. Let's go ahead and do that here, right? On the first iteration 1, I start at 1. Why? Because this one's already sorted by definition. If I only look at an array of the first element, it's sorted, okay? So I need to shift 4 down until sorted. So how many comparisons, total number of comparisons would I do to do that? I would see that, yep, 1, okay, it's out of order, so I swap them. Right? There's only 1, okay? What about the second iteration here? Where at this point I have got something that looks like this now. Let me wipe these out and put in 4 and 42. Right? Now I'm looking at 9. I compare it with 42 to see that it's out of order. Right? I swap them. I then have 9 right here, right here, and I compare it to 4, and I see that they're in order, so I don't swap them. No. And I ended up with how many comparisons here? 2. Now at this point, let me go ahead and erase all this, and I've got 4, 9, and 4, so about it there. 4, 9, and 4. 42, sorry. There we go. And now I'm looking at 4. Okay? How many comparisons do I have to make here to shift it down? 1, 2, and 3. Good. Why that third one? Because you need to know when to stop. Right? And so then I'll have something that, and so let's note that. Number of comps, 3 on iteration 3. But now look at this next iteration here. This is where it really pays off. Right? I've got now 4, 4, 9, 42. 4, 4, 9, and 42. What about 101? How many comparisons do I need to make to shift it down? 1. On iteration, I got lucky, and I only needed to do 1. Kind of like linear search, sometimes you get lucky, right? And you don't have to search anymore. Sometimes you get lucky and you don't have to insert anymore. In fact, if it were already sorted, you wouldn't end up shifting anything. You wouldn't end up swapping anything, and you'd only make about n comparisons. Right? This is the idea behind insertion sort. Why do we call it insertion sort? Because you insert it where it needs to be, exactly. Right? Okay? So, same input collection, right? And we're going to sort it in non-decreasing order. Non-decreasing because 2, 2, 2, 2, 2. Is that increasing? No, it's staying the same, so it's non-decreasing, right? Just a technicality. So check out what I'm doing here. Again, 1 through n here. So I only start at 2 because the first guy, he's already inserted. Right? So I'm going to go from 2 up to n here. I'm going to take x here and save it off as a temporary variable. What I was doing over here was, here's my x. And I'm going to put it over here because I'm going to shift things up. I'm going to shift up, shift up, shift up. And so I'm putting this off into a temporary variable. And in my pseudocode, that's x. Okay? Then I start at an index j here. Right? And I use a while loop. Why do I use a while loop instead of a for loop? Because up front, I don't know how many iterations I'm going to go. I got lucky on this one over here with 102, and I only had to go 1 iteration. So I don't know if it's going to be for each element over here. I'm just going to go ahead and go, while this is out of order, shift it down, shift these things up, shift them up, shift them up. How is that accomplished? Well, first of all, I need to make sure that I don't fall off the edge of my list. Right? So I will break out of this loop if my j ever tumbles off of the beginning of the list. But otherwise, while a sub j sub minus 1 is greater than x, then I will shift it up. Right? This is shift a sub j minus 1 up to a sub j, right? And then decrement j, in other words, j minus minus, right? So that you are going forward into the list. Then at the end, I insert a sub I, which is x, into the list. Right? Good on understanding of the algorithm? Do we want to see it in action here? All right. Let's go ahead and implement it then. Should be straightforward. Right. Insertion sort. There we go. I'm still going to go ahead and go with n here. It's a for loop, but I'm going to start at 1. Remember, my pseudocode here starts at 2, but that's because I'm using 1 indexing. So I will start at 1. and go up to and including the last one. So because the last one does need to know where do need to insert the last one where it needs to be. Right? Let's get rid of all of this for now. Right? So what we're going to do is save off the ith element into a temp variable. And I'm going to go ahead and use x here. Right? List.get I. There we go. Then I will establish an index variable, int j equals, and I'm going to here it's actually going to be I, right? Because I want to look at the ith element and I need to shift it down, or I'm going to, actually no, I don't need to. I can compare it to -1, is that right? Well, we can leave it as I here, right? So while j is greater than 0, right? Why 0 in this case? Over here in the pseudocode it was 1, but again, I need to shift it down by 1 because of 1 indexing. And list.get the previous value, so j minus 1, is greater than x. That means that x needs to shift over so that you can insert x before that. But we're just going to keep shifting, keep shifting, keep shifting, keep shifting. And to do that, let's see, list.set j to list.get j minus 1. Right? We're shifting things up. Right? And then j minus minus, decrement. And I've translated that pseudocode right there. And then at the end, we need to insert a sub I where it needs to be. So, what is it? List.set j to x. Once again, let's kick this down to only 10. And let's make sure that it works. Oh, let's print it out. System.out.println list. Let's make it a little bit easier. Let's go ahead and limit it to at most 100. There we go. 3, 5, 7, 19, 23, 36, dot, 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 dot. Looks good? Okay. Let's go ahead and kick it up to 1,000. Now what was the performance with selection sort before we do that? So this was this was selection. Here's insertion. And let's go ahead and get rid of all this. All right. So before it was 0.024. Let's see if we've beaten that now. 0.023, so no. But small numbers don't really mean anything. Everything's fast when you've got small numbers. Let's go up to 10,000. 0.249. So that's actually slower. Right? Let's find out what happens when we go up to 20,000. 0.885. Oh, am I? No, 20,000. This one was what?
That was 10,000.
Yeah.
No, 40. You did 40.
Was that 40 next? But it was definitely not 0.99 or 0.29. So what was 40,000? Do you remember? It's probably like 4 seconds or so. 3 to 4 seconds.
People in the live stream can go find out.
So wait, we've made a.
There's nobody on the live stream.
Algorithm that's slower than.
Maybe. I mean, that's what it's seeming like to me here. Right? Let's find out. I'm going to go up to, say, 40,000. I do remember 100,000 was 20 seconds. Right? So that's 3.676. Okay. Now let's go up to 100,000. I know that it was 20 seconds here. And let's go up to 100,000 and see if there's a difference. I'm calling insertion sort, right? Yeah. The expectation that I had was that it was going to have the same growth because it's still it's still a quadratic sorting algorithm, but it should have been about half of the performance. And it's not coming out that way. I don't know why. 21.9192. Probably because it's a list, and these operations are really, this set operation is really slow maybe. I'm not sure. But if it were an array in your lab next week, you'll definitely see that this performance is better, right? Why is it better? Let me go ahead and analyze this. Okay. So let's think about this more in terms of like in the middle of the algorithm, right? So here's my array. And in the middle of the algorithm, in other words, at some point for I, right, I have that everything from 1, 2, 3, dot, 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 all the way up to I minus 1 is sorted. Right? Now what we need to do is we need to insert a sub I. This one right here, a sub I. All this is who cares, okay? So on the ith iteration, how many comparisons are made? Huh? It depends, exactly, right? Like you're contemplating, well, I guess we could get lucky, and the best case scenario is what? One, oops. One, to realize that it's where it needs to be. What's the worst case, though? It's going to be I. Careful. I minus 1, minus 2, dot, 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 all the way down to 1 to see that you should insert it right here and shift all this stuff up. So how many elements are among it? I minus 1. Right? Maybe we could do an average case here. What do you think? Just take the naive approach. I minus 1 plus 1 divided by 2. I minus 1, the best case, or the worst case, plus the best case, divided by 2 gives you what? I divided by 2, an expectation. Let's think about the worst case first, though, okay? So for each iteration, each internal loop makes, at most, I minus 1 comparisons. Right? Now let's go back to the outer loop here. How many times do we execute that? For I being 2, 3, 4, all the way up to n. Right? So there's a summation here. I being 2 up to n of I minus 1. Yet another summation to solve. That's all right, we can break it up into 2 summations. I running from 2 up to n of I minus the summation of 1s of I equals 2 up to n. Tell me about the second one here. This is 1 plus 1 plus 1. How many times? Careful, you start at 2. N minus just 1 because you only skipped 1. Right. What about this one right here? That's our old friend, Gauss. But instead of stopping short, we start later. Right? So this is Gauss's formula, n times n minus or plus 1, all over 2, minus 1. Why? Because it's the same summation, but you've skipped 1, so just subtract 1. Okay? All right, solve that. What is it? N times n plus 1 all over 2 minus n minus 2. I don't want to do it. What's the most important term here? One up top, and in particular? N squared. Okay. So this is why we're not getting any performance improvements. It's still going to be, in the worst case, it's still going to be a quadratic. Let's think about the best case, though, the average case. Or the best case, of course, would be n, right? 1 plus 1 plus 1 plus 1. But let's think about the average case. Because now we do have a reason to think maybe there's an engineering reason that we would prefer insertion sort over selection sort. Right? If it's better on average, then sure, let's go with it. that same summation of I running from 2 up to n, but now we're doing only half as many operations. This is equal to, pull that 1/2 out front. I equals 2 up to n of I. There's Gauss's formula again. 1/2 times n plus 1 all over 2 minus 1. Right? Now, at the end of the day, you're still going to have an n squared there. But what is your coefficient sitting out front? Over here, it was probably going to be 1/2 n squared. Over here, what is it? A quarter of n squared plus dot, 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 whatever. Right? So from an engineering perspective, on average, if I actually were to implement these things, then it would probably be twice as fast as selection sort. But the growth rate remains the same, for the same reason that linear growth rates remain the same. Once again, let's look at a plot of these things. What does 1/2 n squared look like? 1/2 n squared. Now, what does 1/4 n squared look like? Above or below this? Oh, careful. 1/4? Smaller. It would be smaller, right? But it would be the exact same rate of growth. Right? Why? Take the first derivative. It's going to be a linear function. Take the first derivative. It's just a linear function with a different coefficient. Right? These have the same exact growth rates. Right? So from a theoretical point of view, it's just as bad. But from an engineering point of view, it's a little bit better. All right, that's good enough for some examples here, but now let's go ahead and think about these things. Right? I told you to look at the first derivative, right, to give you a growth rate. Now let's look at another way that we can quantify a growth rate, right? A rate of growth, right? Using asymptotics. Asymptotics actually predate modern computer science by maybe 100 years or so. It's from calc, so I think it might be Newton actually. I'm not sure. But basically, what we need to do is we need to provide an asymptotic characterization of the complexity function t sub n. Our motivation here is that we want to characterize an algorithm's performance and efficiency with respect to the input size, n. Right? We're only interested in the performance as n tends towards infinity. Right? In other words, larger and larger input sizes, 10,000, 20,000, 40,000, 100,000, as they grow. Right? For small inputs, there's not that much of a difference. Right? When we did the original demonstration up here, right? I don't have my graph here, but I can pull it up, but it'd be the same graph as before. Small values, they're going to be washed out. Everything is fast when it's small, right? And so what we want is a tool that will focus on the growth rate, ignore lower order terms, and ignore constants, because again, the constants are just a function of how fast your computer is. Okay. And for that, we use what is colloquially known as big O analysis. O stands for Omicron, but Omicron, even if you use LaTeX in your lab reports, right? Yes, no? All right. So here's Omicron, there we go, in LaTeX, right? The way that you would do this is, go into math mode here, O, N, right? There we go. It's not, say, all right, it's not, I'm going to go into math mode here, Omicron. Right? Why? Because there is no Omicron. Let me show you.
What's the difference between that?
There is no Omicron. There is no difference. That's why there is no Omicron. You can get Greek letters all day long. For example, lambda. There we go, capital lambda. How did I do that? There's the secret sauce. Come on. There we go. There's the secret lambda with a capital L. Lowercase lambda would look like this. Right? Any other Greek letter that you can think of? I don't know, omega? There we go, and omega. Yep, there's the lowercase. What does the uppercase look like?
Well, it's like the Ohm symbol.
Yeah, oh, ohms. Oh, good, good. Omega is used for Ohm's laws, right? And well, Ohm's laws and like actual measure of ohms. Right? Good. Electrical engineering. Right. All right, so we're going to use big O analysis. Okay. Here's the definition. It's just a math definition. Basically, this comes from calculus almost. Let f and g be two functions. For our purposes, they represent some complexity of two different algorithms, a and b. Suppose that we have, we say that f of n is big O of g of n if there's a positive constant c and an integer n naught such that f of n is bounded by c of g of n for all n greater than or equal to n naught. Right? So this is actually almost a convergence definition, in fact that's what it is. It's just convergence from one direction instead of both directions. Right? Basically it's saying that after a certain point, n naught, that this function will dominate this function, you know, plus minus some constant. Okay? For example, let's just go ahead and take, I don't know, do I have a pre-prepared example here? I don't know. We'll go ahead and take f of n, f of n is equal to n squared plus n. G of n is equal to 1 half, oh actually let's go 1 half here, plus n, and then, 30 n, there we go. Okay. Now let's go ahead and graph this. But remember, we're only interested in quadrant 1. All right? So let's go ahead and think about 1, 2, 3, 4. All right? What is 30n going to look like? Immediately, it's going to be what? Right here. It's going to be very, very stiff. Okay. All right, fine. Come on, start there, go up there. Come on. There, I'll just move it over. Okay, there we go. What about 1 half n squared plus n? At 1, that's going to be what? 1.5? Something like that. At 2, it's going to be 4 plus, but 1 half, so that's 2, that's going to be 4. Something like that. What about at 3? 9, but 1 half, 4.5 plus 3 is going to be 7.5, so something like this, and something like this. So, all right. Now remember that this is a resource, such as time. Okay? What does that tell you about these two different functions? Which one's better? Which one is lower? Lower is better. F of n is lower? Yeah, this is f of n. At least when I'm only looking at small input sizes. Is that going to be true forever? Let's find out. Let's ask Wolfram Alpha to graph these two things for us. Right, so f of n is equal to 0.5 times n squared plus n. G of n is going to be equal to 30n. Please go ahead and graph those for me. All right, and then let's go ahead and go with n equals 0 up to, I don't know, 1,000. Oh, come on. Graph. Graph. I have to force you to graph it. There we go. Plot. There. Right. When I pull back out and look at on the scale of 0 to 1,000 here. Do you get the same picture? When I only focused in here on small input sizes, 0 to 4, it looks like, oh, well, g of n, it's much steeper. It's worse, right? Because it's above the line. Lower is better. That means it's a lower resource measure. But at some point in here, right, this function is clearly worse, right? And then this linear function is down here. What is that point right there? The intersection. So how do I determine where it is? Let's go ahead and zoom in on it by 100. Oh, okay, now I start seeing it. It's where? It's a little less than 60, between 50 and 60. So let's go ahead and go from 50 to 60, see if we can zero in on that. Okay, there it's almost at 58 or so. So let's go ahead and kick it up another notch here to 57, up to 60.
Hey, isn't there an equation for finding
Yeah,
intersections?
is there? You tell me. How do you tell when two equations are the same? For what n? So let's go ahead and take those two equations. 1/2 n squared plus n is equal to 30n for what n? This should be middle school stuff now. Sorry. Copying down stuff correctly is also middle school stuff.
The two quadratic that's either 0 or 58.
Oh, okay. So you jumped immediately to the solution. How did you go about doing that?
Just subtract it over, you get 1
Good.
n squared minus 29, and then you
Oops.
break that, that's equal to 0.
Plus 0 is equal to 0. There we go, right? And now that's a quadratic equation, and it's set equal to 0. How do you find values for n that satisfy that?
You can factor it, or you can
Okay, good. You can in this case you can factor out an n, right? One of those n is going to be 0, and then once you factor that out, then you have 1/2 n minus 29 is equal to 0. Then you solve for n there. Right? But what if it was more general? Right? What if you had? Let's go ahead and go with 1/2 n minus 29n plus 0. What other tool do you have to bring to bear?
the quadratic one.
Yep. N is equal to negative b plus minus square root of b squared minus 4ac. This is correct, right?
Yep.
Over 2a.
Yep.
Plug that in and you'll get, what were the values? N is equal to 0 or 58. Now, that's the two locations in which they intersect, because it's a quadratic formula. Right, let me go to -5 to 60 here. And let's plot that out. You'll see that they intersect right here and that they intersect right here. Which intersection point are we interested in? Clearly this one, right? Why? Because when they, of course they intersect at 0. Who cares? Small input sizes. I want to know at what point do they intersect, and then they will never ever meet again. This one will always be greater than that other one. Right? And that's just algebra. So 55 up to 1, well, let's go 500, right? There we go. So after that point down here somewhere, then it's clear that n squared is going to dominate. And this one will always be better. Even though the coefficient is much larger for small input sizes, sure, this one does better. But for all reasonable size inputs after that, after size 58, this one is definitely going to be doing better. How does that fit in our definition? For this particular example, what was n naught? After a certain point, right? N naught was 58 for us. Right, you said 58, right? Yeah, 58. Right? All right, so n naught being 58, then what is it? 30n is going to be less than or equal to c of 1/2 n squared plus n, right? For c being 1, right? Because we just did the algebra. There's another way that we could have done this. what we could have done is, okay, well, what I'll do is I'll start at 0 here. I'll suppose that my n naught is 0, right? Because you, in this equation here, you actually have two unknowns. You have n naught. We found n naught. You also have c. What if we fixed, basically implicitly what we did was we fixed c to be 1, because when I wrote out that f of n is equal to g of n, I was saying that c here is equal to 1. I just didn't say it, right? What if we went the other way? What if we set n naught to be 0, and we wanted to make sure that the intersection point was right there at the origin? Right? What would that look like over here? So remember that we've got f of n is equal to 1/2 n squared plus n, and g of n is equal to 30n. Right? You switch these around, f, g, whatever, right? In fact, let me do that. There you go. There. We want to show that this one that seems like it's lower and this one that seems like it's higher, but only up to a certain point here, 58 for c being 1, right? What if we wanted to shift this down so that the crossover point was right here at the origin instead? What could we do to one of these functions? So this is the original g of n. This is f of n. Right? What can you do here to manipulate these two things? Here, let me show you. What does two GMNs look like?
It's going to be tighter to the y-axis.
N squared, so it's n squared plus 2n, all right? And what is that going to look like? Tighter to the x-axis. Maybe it still dips below here for a little bit and then goes up like this. Okay, there, 2g of n. Right. So maybe that shifts this crossover point here over here. Do that again. What does 3g of n look like? Maybe the crossover point has now shifted down here. In other words, by making this bigger and bigger and bigger, right, you are changing the crossover point until it gets down to n naught being 0. Right? What does that look like algebraically? Right? So we want to show that f of n is less than or equal to, c g of n for all n not greater than or equal to 0. Okay? In other words, I want to show that 30n is less than or equal to some c n squared, 1/2 n squared plus n. There we go. Right. Dot, dot, dot. So start with 30n. How can I make it bigger? Well, I'm multiplying by what?
A specific number or bigger? Like a 2?
2? Okay. So then I get 60n? Okay. I could do that. That's not going to get me to where I want it to look like this, though.
Oh, I track now, sorry.
So how could I make it bigger? What if I like your idea of multiply it by 60. Let's just multiply it by something else. N squared, like n. Why? Why can we do that? If we were to multiply by a negative value, would that inequality hold?
No.
No. We're not multiplying it by a negative value. Why? We're only ever considering the positive numbers. Right? So for all n greater than or equal to 0. Right? Okay, it looks something like this up here. Okay. How can I make it even bigger? I could add as well. 30n squared plus n. Right? Why? Because, again, n is positive. Right? It's looking somewhat like this now. I could go ahead and factor out a 15. and this is now 1/2 n squared plus n, but I factor out a 15, so it'd be like 1/15. It almost looks like that, so maybe I shouldn't have added an n. What should I have added? Okay, more is better, right? It's not you're not going to make it any smaller by adding more. 15n. All right, that's equal to.
It actually has to be 60n.
Oh, okay. Is that right? Because you're going to factor out a 30. Oh, you're going to factor out a 15.
Factor out of 15, right now you're gonna have 2n squared.
Oh, that's right. That's right. Okay. So factor out what do I need? I'm going to have to factor out what?
That's fine,
15.
that's-
Yeah. So this is right, right?
Okay.
Yeah. This is equal to 15 times. Wait, no.
2n squared.
2n squared. But I wanted 1/2 n squared
Okay, so
plus
60,
n.
full 60.
All right. But you get the idea. I'll come up with. That's why these things. Yeah, I just threw this together on the fly, right? This you usually come up with nice polynomials that match in advance, exactly. And you stay away from cubics,
Oh, okay.
quadratics. Anything above 2. Why? Because then you lose the ability to use the quadratic formula. Do you know how to factor cubics off the top of your head?
No.
Okay, but there is a rule to do it,
Yes.
right? Do you know how to factor out a degree 15 polynomial?
Yes.
There you go, you pick up your, oh, is that a TI? What is that?
And TI inspired.
Okay.
You'll do a 50 degree.
All right, cool, all right. Well, by the time that you've typed it into that calculator,
Oh,
you could have done it in like Wolfram Alpha or something, add half as much time.
Very good.
But anyway, you get the idea. We'll get way more practice when we do revisit this next week in class. But otherwise, that's the definition. Right? It's simply that after a certain point, when you're comparing two functions, this function will dominate this function, and they'll never cross again. Right? So that immediately rules out, say, sinusoidals kind of stuff, right? That's really weird. Can you imagine an algorithm that, oh, for this one it's good performance, for that one it's bad performance, good performance, bad performance? I can't imagine that. So that's why we're only considering monotone increasing functions. Right. All right. Oh, we did have somebody eventually. Okay. Anyway, have a good weekend.